theoretical nanoscience, especially quantum transport in graphene, topological insulators, and others. Then in quantum information, we mainly focus on quantum walks. Today, I will be speaking about that. And then we have another branch on game theory. So today I have planned to speak about all the past works that I have been involved in my group. And I will go in this sequence. First, I will talk about discrete-time quantum walks, and where we implement what is called the Parrondo game or the Parrondo paradox. And most of the papers are on that itself. Some aspects of Parrondo paradox and quantum walks. And later on, I will be talking about something we have done very recently on quantum stochastic walks using photosynthetic complexes. Okay. So before I start with Parrondo games, let me just introduce what are Parrondo games. Okay. So Parrondo games are two games in which the probability of losing is greater than the probability of winning. So if played in a particular deterministic or random sequence. So let's say A is some player and there is some game. And in that game, if the amount of money that say A has, so A is a player which starts with some amount of money, kind of a gambler. So he gains 3 rupees if the total money that he has is odd, and he will lose 5 rupees if the total money that he has is odd. So it's an odd number. So if you can see the gain and the loss, so at each time step when he plays this game 1, ultimately in the infinite time limit, he will lose money. And game 2, he's sure shot going to lose money because at every turn of the game, he will lose a rupee. Now, we can see that here, if we start say with 200, which is an even sum, he will end up with 203 after the first time step. Then in the second time step, he would lose 5 rupees because now he has an odd number, 203. And likewise, when he plays for a long time, he will lose all his money. And game 2, as we have seen, he loses a rupee at every time step. And so at 200th time step, he would have lost all his money. Now let's play them in a different sequence. Let's say he plays game 1 on the first time step, then goes to game 2, then goes to game 1, and so on and so forth. So again, he starts with this even sum of money that's 200 rupees. And after the first time step, he would have 203 rupees. He has played game 1. But then in the next turn, he would have 202 rupees because he's playing game 2 and he loses a single rupee. Then he again turns to game 1. He again has even number and he gets a gain of 3 rupees. So he gets on to 205. So likewise, when you play this game in this sequence, game 1, game 2, game 1, game 2, you would find that in the infinite time limit, he would never lose. He never loses any money. He always gains money. So this was first conceptualized in a Nature paper by these two authors, Hammer and Abbott, under this nice title, Losing Strategies Can Win by Parrondo's Paradox. So this Parrondo's Paradox actually, or Parrondo's game, was first visualized by JMR Parrondo himself, and he was talking in the context of cellular transport. So cellular transport in any animal or plant cell, food or energy transport is always against a very big applied potential bias. So people speculated, what is the way that cell transport occurs if there is such a huge activation energy has to overcome? Now, the only way one can think of this is, let's say I have a ratchet like potential, and there is an uphill slope. Let's say, in this case, in this figure A, you see figure 1A. So there is no way that you can have a particle transport against this huge barrier. You will always be, the current of particles, say, will always flow to the right. It will never flow to the left. And similarly for this kind of potential also. So A is a kind of a linear potential and B is a periodic potential, but it's a damped periodic potential. So always the particle flow would be to the right in both these cases. But if you do the Langevin dynamics, in case where the potential flashes between this linear one and the periodic one, as it's shown here, then you see there is a net particle transport up the slope to the left. And it's very similar to what we saw with the person who was gaining money when he was playing two losing strategies. So two losing strategies played alternately can win you money. And likewise, there can be particle transport against the applied bias if you are switching between two potentials, which individually can never give you particle transport against the bias. And this was first conceptualized by Parrondo in these two papers, and later on this went on and to many other fields, especially in the quantum context. So our motivation was clear. Can we see this in the quantum context using quantum box? So before I go to playing Parrondo game in quantum box, I will just give you a brief introduction to quantum box. So we all know what's a classical random walk. You have a coin, you toss it. If it's a head, you say go right. If it's tails, you go left. And likewise, if you start at, say, you have on a 1D line and you toss this coin, there is 50% probability of going to the left or right. And then again at time step 1, you again toss it. And then there is a 25% probability of going to position this -2. And at this position, of course, the probability is reinforced. So you have about 50% probability to coming back to 0. And then again, 25% probability to go to position. And likewise, at every time step, if you toss, you will have these kind of probabilities. And you will see that for a long time limit, say here, if you plot for time step 100, you'll see some kind of a binomial or a Gaussian distribution arising. So this is for probability at time step 100, and these are the site indices. So the mean of this probability distribution is always at site 0, and the standard deviation goes as square root of t, where t is the number of time steps. Here it's 100, so it goes around 10, which is the standard deviation. So how much is the spread of your particle from where it started from? Now the same thing, you can quantize this and look at it as a discrete time random walk. So you have some quantum state living in a Hilbert space. And now this Hilbert space is a tensor product of this coin Hilbert space and the position Hilbert space. Now the coin has, as before, is considered to be a qubit. So you have 0 and 1 states. And the position is, say we have a 1-day line, so it's from -infinity to infinity. And so for the coin, you can take any unitary operator. For example, if you take the Hadamard here, and then you evolve it in time. So the unitary operator is the coin operator, and acting on the state of the particle or the state of the qubit. The state of the qubit is now written. The first ket is for the coin space. The second ket here, n equals 0, is for the position space. So it's a tensor product of its coin and position space. And then you apply this unitary at each time step, and then the particle evolves in time, and you calculate the probability by taking the inner product of psi t with itself, find out where it is at time steps at 2, 3, 4, 5, like this. And when you do that simple calculation, you will find that at t equals to 1, if you start at 0, so this is a coin which is at a 0 state. At position 0, you start, and then you calculate the probability with this Hadamard. You operate this Hadamard. You no longer toss a coin, but you operate the Hadamard, and then calculate and then do the shift likewise, and then find out the probability. So you again get 50% probability to have shifted to the left or 50% probability to shift to the right. Similarly, at time step equal to 2, you will say it is mirroring the classical random walk. But then at time step equal to 3, there emerges a divergence between the classical random walk and the discrete time quantum walk. You see that now there's some kind of asymmetry building up. So here the probability is 1/8, 1/8. Here it's 5/8. So it has reinforced it because of mutual constructive interference and constructive interference. We see that the probability to find the walker at site 1 is rather large as compared to what you would have for the classical random walk. And similarly, this asymmetry grows and grows. For time step 5, you have here somewhere at site 3, 17/32. Okay. So likewise, you can calculate for say 100 time steps, and you will find some kind of a asymmetric distribution shown here. So the mean is somewhere here, not at 0, quite different from a classical random walk, but the standard deviation goes as t, not as square root of t. So the quantum walker spreads quadratically faster than the classical random walk. Now you can restore this symmetry and get the mean to be at 0 if you take a superposition. So if you take a superposition of the initial point state of 0 plus 1, then you will see that you will get a symmetric distribution. But even here, even the mean is at 0, the standard deviation again goes as t. So the main difference which we saw for the discrete time quantum walk as opposed to the classical random walk is the spread is quadratically faster. Okay. So now we plan to implement the Parrondo game on a discrete time quantum with a discrete time quantum walk. So the first thing, if you choose, is how do we define a win and a loss? So if you have the median of your probability distribution to be somewhere at the left of 0, you will define it as a loss. And if you have the median of the probability distribution somewhere at the right, you will define it as a win. Okay. So this is how we define a loss or a win in our 1D quantum walk. So we have these coin operators. Now we take general unitaries. Again, we take the initial state of the walker at 0 and the coin as a superposition. And similarly, the shift operator can be written as if you have at 0, you go to the right, and if it's at 1, you go to the left. And this shift operator can be succinctly written as a sum over this S. This is the coin state as this, and quite clearly you can see. And then you play two unitaries. So a unitary, say UA, represents game A, and we operate it at times all say even time steps, and at all odd time steps we operate the unitary B. So unitary A and unitary B are our two games, and we play alternately and check whether we get some kind of a Parrondo paradox for the discrete time quantum walk. So very similar to what we have seen, the final state would be after n number of time steps would be this unitary to the power n with the initial state. Okay. So what do we see? Now, when we play only unitary A or only unitary B, we see that the median is always to the left. So there is no chance of winning. The game is always you end up losing. But if you play alternately, for example, not AB, but if you play this game ABB, ABBB, you will see there is a small probability of winning for a few time steps around 50 to 100, between 50 to 100. But in the larger time limit or in the asymptotic time limit, you always lose. There is no probability of finding the walker to the right. So initially there were some papers which predicted Parrondo's games, but with a few number of time steps. But later on in these papers, it was found that in the asymptotic limit they don't hold, and you have always a losing game. So Parrendo's paradox was not seen with qubits in the asymptotic limit. So our motivation was then, if we can implement Parrendo's paradox in the asymptotic limit, that is the large time limit, and what do we need to do that? So our motivation, as I said, was to find circumstances for the existence of a genuine Parrendo's paradox, not a Parrendo's paradox which shows itself at small time steps and then disappears in the long time limit, but is sustained over a long time scale. So we take, instead of a single qubit, we take the entangled state of 2 qubits. So the entangled state of 2 qubits, if you see, is now given here. This for theta is pi by 2 is actually a Bell state. And the position of the walker now, so there are now 2 walkers, but they are now fixed at position 0. But the coin state is now of the 2 walkers is entangled, or could be entangled or non-entangled, whatever. So the coin now is a bipartite system, and now we play this game on each of the 2 coins. So we can play game A on the first coin or the first walker, and game B on the second coin or the second walker, or we can alternate between A, B on the first walker and B, A on the second walker, and check whether we can see a Parrendo's paradox or not. So now, because our Hilbert space has enlarged between the 2D Hilbert space of a qubit, now we will work in the 4-dimensional Hilbert space of this entangled coin. So our shift operator also has changed. So now for this 2 coin shift operator, we have this 0, 0, 0, 1, 1, 0, and 1, 1. And we have, unlike the single qubit shift, you have the shift to the right or the shift to the left only for these 0, 0 and 1, 1 states. But in case of 0, 1 and 1, 0, the particle doesn't move, or the walker doesn't move. The 2 walkers, I mean, don't move, and they are transfixed at that position itself. The full evolution operator now for our 2 qubit state is given as this. And finally, after n time steps, we have the same form, the unitary operator to the power n to the initial state. Okay, and then you take the inner product with itself to calculate the probabilities at each time step. So what do we see here? So what we see here is, if you play this game of AB on the first coin and BA on the second coin with a partially entangled state like this, we get the median to be at the right side, that is for x greater than 0, even in the long time limit. So we are plotting for time step 1600. So in the asymptotic limit also we see that we get a Parrendo's paradox, because if we play the sequence A on the first coin and B, you always get the median, which is somewhere to the left of the origin. So always you find here that if you play only 2 of these games, A and B, you always end up on the left side of the origin. But if you alternate between them, AB on the first and BA on the second, you end up on the right side of the origin, and therefore you win in the long time limit. It's important to note. So we showed in this paper, this was with Jishnu, one of my master student, we showed that you could see a Parrendo's paradox in the asymptotic limit in a quantum picture. Okay. And now, what are the reasons for this? So to do that, we also plotted the median as well as the concurrence. And we see that the median is to the right, as shown here, even when the concurrence goes to 0. So entangled coins or entanglement has no specific purpose in our case. We could have just as easily chosen just 2 coins which have 0 entanglement, and we could have seen Parrendo's paradox. And of course, when I see the win is defined as 2 coins going to the left and a game played in sequential order ABAB on the either of coin going to the right. This then entails the question, what about the initial state of the coin? Let's say I take the initial state 1, 1. Do I get that? So initially I had some partially entangled state and I showed you. But if I take an initial state 1, 1. So if I take an initial state 1, 1, similar to previous cases, I will see that there is no Parrendo's paradox in the asymptotic limit. So initially, for a large number of time states, you see a Parrendo's paradox, but in the asymptotic limit, beyond say some 800 time steps, you see the Parrendo's paradox ceases to exist. Okay, so even if here you are losing, here again you start losing. Okay, but here what matters really is the two things: the initial state and the wait state. Here we have defined the wait state as this in the shift operator. If we choose a different wait state, let's say here we have a single wait state. So here you go, if you are at 0, 0, you go to the right. If you are 0, 1 also, you go to the right. If you are 1, 0, you stay put. And if you are 1, 1, you go 2 steps to the left. In such a shift operator, you'll see again the 1, 1 state now gives you a winning Parrendo's paradox. So if you play 1, 1 with the initial state, the median now goes to the right, while single coins A and B, you will end up somewhere to the left of the origin. So we generalize this and we find that the most plausible reason behind observing this Parrendo paradox with two entangled or non-entangled initial state is the introduction of some kind of asymmetry either in the initial coin state or in the shift operator with 1 or 2 wait states. So the wait states here matter. Depending on the wait states, we'll either get a Parrendo's paradox or we don't get. So our work can be considered as a demonstration of a quantum ratchet too. So what Parrendo initially proposed as a classical ratchet where particles flow against the applied bias, if they flash between two kinds of potentials. Here also you can see that in this quantum walk picture with two unitaries where you land up on the left, but when you play them in some sequential manner like this ABAB or BABA, you always end up to the right of the origin. Okay. So taking inspiration from this, we looked at a Qutrit state also. So Qutrit differs from a qubit. Now it's a 3 quantum state quantum state. So it has a 1 and a 0 and a 2, and it's now a 3D Hilbert space for the coin. And similar to that, we define a position space on a 1D line, and we play the shift operator. The shift operator now is a bit different. The shift operator, depending upon the state, this is the wait state for 1. And if it's at 0, it goes to the right. And if it's at 2, it goes to the left. Here also, because of the crucial role played by the wait state, you again see a Parrendo paradox. And of course, the coin operator here, in general, if people who work in particle physics would know this, they come from the CKM and all those matrices for elementary particles. So you can form these general coin operators and play around with these angles, and you can see different kinds of Parrendo's paradox emerging for different sequences. Okay, so I'm not going here, and you can see this. So here we have AAA, and you end up somewhere on the left, and you play BBBB, again you end up somewhere on the left, but when you interchange ABAB, or sorry, BABA, you end up somewhere on the right. So, so with the initial state of a Qutrit also, we can see a Parrendo's paradox. So when this paper was published, we got a lot of media attention. There were 2 articles in Physog and Life Science, which explained this work for a completely general audience. And if you want to read more about it, you can look at this EPL paper. And subsequently in EPL, this paper was a highlight of 2018. Now, not only we can see games where we have particles either ending up to the right or to the left as examples of Parrendo's paradox, we can also go to chaos and order, where we have seen them classically. So what do I mean by this? So again, Parrondo himself, in working with some of his collaborators here, they published in PRL some time back in 2002 that we can have two chaotic systems. When they are combined, they can give rise to an ordered system. So our idea was, and the same Parrondo principle occurs here, where we had two losing games being combined to get a winning game. Here, two chaotic systems can be combined to get some ordered system out of it. So our motivation was, can we see this with quantum walks? And to do that, we choose a cyclic graph. And if you want to read more, you can look at this Qutrit paper. And it's general, we showed it for both 3-cycle and 4-cycle graphs. And we showed that if we have a quantum walk on a cycle, let's say the 3-cycle here, there are 3 sites only. And if it returns periodically to a particular position, say the origin, then we say it is ordered or periodic walk. But after an infinite number of steps, if there is no a return to its original position, then of course it is a chaotic walk. Okay, and we showed in this work that if we have a coin operator which goes as AAA, there is never a probability of coming back to the origin. Say we start from the origin, there's never a 100% probability of coming back to the origin, and therefore this is a chaotic walk. And there is another chaotic walk with a different unitary coin, say BBBB. And again, there is no probability, 100% probability of coming back to the origin. So there is no periodicity here. So it's again a chaotic walk. But if we combine them and play AABB, we get a periodic quantum walk with a period of around, say, 5 or 10, whatever. So we can see this combination of two quantum chaotic walks leading to an ordered quantum walk or a periodic quantum walk, just as they had predicted for classically what was seen. So to understand what is happening in detail, so we again have the very similar coin operators, the most general coin unitary operators. But now, since we are having a quantum walk on a circle of say k sites, we have this mod operator working. So this ensures that you are always in some site within that range of k. And of course, again, you apply the unitary operator, which is the shift and the coin. And for n number of steps, you take the to the power n of this unitary operator to get your final state. Now, as we defined, if the walker returns to its initial state after n time steps, then the walker is periodic or ordered. And for an ordered quantum walk, what we'll see that this unitary is exactly equal to the identity operator. Okay, so U and K would be equal to the identity operator for a periodic quantum walk. I can define my eigenvectors of this unitary as some x ket and the corresponding eigenvalue as lambdas. And I can try to express my initial state in the eigenbasis of this unitary operator. Okay, so if I do that after applying UKN times, I will have this, because this now has been expressed in terms of its eigenvalue and its eigenvector. So we'll have the condition of periodicity as the eigenvalue raised to the power n, because for the n time steps is 1. Okay, and now the identity here is of dimensions 2k, because k is the number of sites in your cycle and 2 is for the states of your coin. So the dimension has changed. So if I have a 3-cycle graph, I will have a unitary operator with dimension 6. Okay. So what is happening and how do we go forward? Okay. So UK, if you see, I've written here for the three-site graph, is a circulant graph. What does a circulant graph means? So that means that each block circulates in this matrix. Therefore, it's called a circulant matrix. Now, the nice thing about the circulant matrix is that these circulant matrix can be simultaneously diagonalized by what is called the commensurate Fourier matrix. So the commensurate Fourier matrix is defined as M, and each of these Fourier matrix elements is given as this. So you can diagonalize this unitary and find that it turns completely block diagonal, and each of the block diagonal gives you eigenvalues which are repeated eigenvalues. So each of these block diagonals gives you identical eigenvalues. And as we have seen, the identical eigenvalues, the eigenvalue raised to the power n is nothing but identity. So you can take the sum of these two eigenvalues of each block matrix, that we can equate it to a periodic quantum walk and check what kind of sequences will land me in a will give me from chaotic to periodic quantum walk. We can frame some simultaneous equations and solve them and get the conditions for getting a periodic quantum walk. Okay. So is everything clear till now? Are there any questions? No. Fine. So if I do it on a 3-cycle graph, which with 3 sides, I have my 3 coins as these unitaries. Now it's not just the coin, but the shift, and I take the whole thing to be the game A. The game B is a different coin operator, but the same shift. And then the game C, which gives me a periodic quantum walk, is this C. So my idea is, first I play this game C and find out the condition on this rho alpha beta, which are the parameters of my coin matrix, and find out for which parameters I get a periodic quantum walk. And then I check for A and B. A and B, of course, are some rho 1 and alpha 1, beta 1, which give you a chaotic quantum walk. And then I check where this A, B, BA, whatever combinations, I equate it to these conditions on C, these eigenvalue conditions of the game C, and find out. And when I solve it simultaneously, I find out the condition which gives me a periodic quantum walk. Okay. So the quantum walk obtained from the unitary C gives an ordered quantum walk with a period n, while the unitaries A and B lead to chaotic quantum walks. So our aim, as I said, is to find a suitable combination of A and B unitaries, which would give an ordered or periodic quantum walk. So after I calculate the eigenvalues by diagonalizing my unitary, let's say I consider AB as my Parrondo sequence. So both A and B individually are chaotic quantum walks, and I suppose my and check whether I can get a Parrondo sequence. I do it first for AB, and then I diagonalize using this commensurate Fourier matrix and find the eigenvalues. So this is for the block 1 of the 3-cycle graph, and I do this AB, and I get this eigenvalue for this AB one. Similarly for CC, I get this. Now CC is a periodic quantum walk, while AB I have no idea. If I solve and I get a condition, then it may be. So when I equate the eigenvalues, I get this condition, but I see that the only condition which solves it is the trivial condition, that rho 1 and rho 2 are equal to rho. That means only if both the coins are equal to C, then you get a periodic quantum. Well, that's neither here nor there, because I want some different condition on A and B, which gives me a periodic quantum walk. So obviously with Parrondo strategy, Parrondo sequence AB, this is not possible. Okay, now let me try another strategy, which is AABB on the same 3-cycle graph. And now I, using my commensurate Fourier matrix, diagonalize AABB Parrondo sequence, and I get this large eigenvalue. And then I equate it with, again, the CCCC, which is a periodic quantum walk, to check if I get. Now, this gives a non-trivial solution. So when we solve this, we get a non-trivial ρ1 and ρ2 for a definite rho. Okay? And I plot this here. So I have my game A as some unitary with ρ1. I take all the other parameters, alpha 1, alpha 2, beta 1, beta 2 is 0. Game B, again, is a chaotic quantum walk, which I show here. And these are equal to this periodic quantum walk given by this for a 3-cycle graph. And I see that when you play AAA, there is no probability whatsoever coming back to the origin. But when you play AABB in this sequence, AABB, AABB likewise, you always have 100% probability of coming back to the origin. And the period of this quantum walk is around time step 20. So with 2 chaotic quantum walks, we have generated an ordered periodic quantum walk using this method. Okay, fine. Now we generalized it and showed it in a 4-cycle graph as well. And only the eigenvalues and all will become more complicated, but you can subsequently show it for any nk cycle graph actually. It's easy to show. Okay, so now a question may arise, since we have plotted only till 200 steps in both AAA and BBB. What if the time period exceeds 200? Let's say time period is 300 or 400, whatever. So how do you know that these are exactly chaotic? Okay, so one way to find out whether we have a real chaotic system or not is to calculate the Lyapunov exponent. So if a positive value of the Lyapunov exponent implies that the quantum walk is chaotic, while if the Lyapunov exponent lambda here is 0, then it is not periodic or non-chaotic. And just like previously, we have an initial state, psi T0. T0 is your initial time step, and we evolve it in time. And then if we have a unitary operator, which is UC, it gives a chaotic quantum walk, and UP, it generates a periodic quantum walk. And likewise, if it is a periodic unitary, then we have the condition that UP at TP time steps would be equal to the identity, but UC at T time steps will now be equal to psi T0 for all T. From these two definitions, we can define what is called a distance state. So how far is the distance of your psi at time step T from T0? And obviously, psi d would be 0 for u equals to UP, but psi d will never be equal to 0 for the chaotic unitary. And from this distance state, you can calculate what is called the probability distance function, which we define here. And in the chaotic case, for which lambda is greater than 0, the maximal possible value of this probability distance would be 2, while for the periodic case, it would be at t equals to that time period would be 0. So lambda you can calculate using this, and this paper does that actually. Calculate this Lyapunov exponent for quantum walkers, and we use that. And for our 3-cycle graph, we check for AAA, game AAA, we get a lambda which is somewhere 0.012, so it's definitely a chaotic walk. For BBBB, we again get 0. So it's again a chaotic walk. But for the process AABB, it is 0. Lambda is 0 for exactly 20 time steps, which is the time period of that quantum walk. Okay. So if you want to know more, you can look at our paper here. So one of the applications of our study is in quantum cryptography and also in quantum chaos control, actually. So chaos by itself is not useful for us, but if we can control the chaos, then it becomes useful. And one way to do it is, as we have shown in our work, that if you have a chaotic system, you add another chaotic system to it and get something periodic out of it. So let's say we have 2 persons, Alice and Bob, and who want to transfer a message. And this message is any of these numbers, 0, 1, or 2, to Alice. So Alice first makes a public key using the unitary operator B and the state of the walker. So S is your coin state and L is your position on the cyclic graph, and she does BB and sends that to the Bob. So B is the unitary operator, as we have seen, which generates a chaotic quantum walk, and this is the public key. And L is the Walker state, and S is your coin state. Now we know that with another unitary A, and we have seen AABB generate a periodic quantum walk, but AA by itself generates a chaotic quantum walk. So if I do this 5 times AABB at time step t equals to 20, I end up with identity. That means the periodicity of the quantum walk is 20. So after Alice generates this chaotic state, she uses it as the public key and sends it to Bob. And Bob then, after receiving this public key, encodes the message. So the message is any one of 0, 1, 2, and he does that. And this is very similar to the shift operator on a cyclic graph. And then it encodes this message. And after that, sends it back to Alice. Alice then decrypts the message by applying AABB 4 times into AA. As we know, this is your D, and already BB is the public key. This gives you the identity. And finally, Alice makes a measurement, II, and gets the message M prime. And this message we can recover by doing this mod 3, because it's a 3-cycle graph, M prime minus L. Mod 3, you can recover the message. Okay. So this is the application of our work. So you can hide your messages in the chaos, but then retrieve it by adding more chaos to it, because you know that 2 chaotic systems, as we have shown here, can add up and should give you a periodic or a ordered system. So to conclude, this is the first part of my talk. A periodic quantum walk was obtained by repeatedly applying AABB, even when coins A and B produced chaotic quantum walks. And the work shows that it's possible to design a quantum periodic signal from 2 quantum chaotic signals. And that means also that the reverse process is true. We can break a periodic quantum signal into 2 or more quantum chaotic signals. And before that, I showed that with the aid of Qutrit, or 2 entangled or non-entangled qubits or partially entangled qubits, we can successfully implement a true Parrendo's paradox in the infinite time or in the asymptotic limit by exploiting what is called the wake state of the shift operator. And quantum Parrendo's games, as we all know, play an important role in ratchets, as do classical Parrendo games. And they provide a mechanism of particle transport against an applied bias. And in quantum analogy to it, we can show that for quantum Brownian heat engines or thermal engines, you can show particle transport against an applied bias from this quantum walk picture. Okay. So are there any questions on the first part of my talk? Okay. If there are no, I go to the second part. So this I will spend very few moments on it. This is a work with another of my students where we showed that we can generate highly entangled state, but single particle entanglement. So entanglement is not only between 2 particles, entanglement can be between 2 degrees of freedom of the same particle. So let's say we have an electron in this position or coin space, and we can have entanglement between the position and the coin space here. And that's what we show here in this work. We calculate the Schmidt rank and find that with Parrendo sequences, while with, say, HHHH, where we apply the Hadamard or the X, which is the NOT operator, we get some entanglement which is less than 1, which is 100%. But with a combination of XHH, a Parrendo core sequence, XHH, XHH, repeating it likewise, for a large number of time steps, we go and get almost maximally entangled state. Of course, this is single particle entanglement within the different degrees of freedom. And there have been many works on this approach to generate a single particle entanglement. And we show that using Parrendo sequences, we can get almost at 5 steps, always maximal entanglement. Okay. So till now, we have considered only discrete time quantum walks where we have a coin as well as a position space. In contrast to that, there are something called continuous time quantum walks where you don't have a coin. So you just have a position and you evolve a walker. So walker doesn't have a coin. And this, for example, discrete time quantum walks on a line or 2D lattices, they're very easy to calculate. But if you have some kind of a network, say a scale-free network or a kind of a Erdos-Renyi or some kind of arbitrary network where the degree distribution is not fixed. In a 1D line, you have each vertex site connected to its nearest neighbor with edges. But say we have a network where there are some vertex sites which are connected to many other vertex sites through edges, and there are some other vertex sites which are not connected at all or very few connections. In those kind of circumstances, when there are arbitrary number of vertices connecting with edges and with other vertices, then having distinct coins for each of those vertices in networks is really cumbersome and almost unwieldy and very difficult actually. So in those cases, you evolve the whole Hamiltonian, or what we call the adjacency matrix of the network, in time. So we know that if your Hamiltonian is independent of time, then the unitary corresponding to it is just minus IHT, and you can evolve it in time and find out at some time step, last time step, what is the final state. So if you want to give an analogy with your 1D quantum walk, discrete time quantum walk, then you have something like this, where you have some site energy to gamma here, and then each of your sites is connected to its next nearest neighbor with some edge with strength gamma. Okay, so this is like a 1D line. And you can calculate the probability. Analytically, actually, you can calculate it and it comes near like the Bessel function. And if you plot the probability distribution, you get a symmetric probability distribution. But again, the standard deviation, here it's for 100 times step, is proportional to t. Same like in the discrete time quantum walk for a 1D line. Okay. Okay. So in the final part of my talk, I will go to something called quantum stochastic walks. But before that, I have to introduce the picture of quantum transport in FMO, photosynthetic complexes. Okay. So your Engel was a student in 2007, and he was doing some electron spectroscopy, and he showed, and he saw, and he was looking at some photosynthetic complex called the Fena-Matthew-Solson complex that is available in green sulfur bacteria. So what he did was he fired pulses of laser light into the photosynthetic complex and got the response. And when he plotted this signal strength in time, he saw some kind of beat pattern, which arose. Of course, he did this experiment at very low temperatures, at liquid nitrogen temperature. And he found that this beat pattern lasted for around 600 femtoseconds. Now, this is quite large because it's well known that in the photosynthetic process, in the process of photosynthesis, light is absorbed by chromophocytes and sent into the reaction center in less than, say, 100 or very few femtoseconds. So if some kind of a quantum process lasting till 600 femtoseconds, then this begs the question, is quantum phenomena responsible for the high efficiency of the photosynthetic process? The photosynthetic process is one of the processes where there is 100% conversion of photon light to energy. Now, if we can do something artificially, that would be great, because artificially capturing photon and converting to energy is really, the efficiency is really bad. But leaves converted with 100% efficiency. So people speculated that maybe quantum phenomena is working in even tiny leaves at temperatures around 300 Kelvin. Okay. So if you read this book by John Joe McFadden and Jimel Khalili, it's a very nice introduction to what I'm saying here. So those experiments by Engel were with isolated FMO complexes and were at 77 Kelvin. So people said that maybe it is because of the temperature that something quantum is going on. So how relevant were these to a room temperature like 300 Kelvin or something? Now, in later on, people here, Ian Mercer and all, looked at different photosynthetic complexes. So they also saw that at normal ambient temperatures, in which plants perform photosynthesis, they could see some kind of a beat pattern. Even in 2010, again, another person, Greg Scholes, also showed that. And then Engel again came back to the same FMO complex, and he showed that again at around 300 Kelvin, he could see the beat pattern. So there is a whole sequence of such experiments which showed that possibly quantum effects are responsible for the high efficiency of the photosynthetic process. The theory, which was first propounded by Seth Lloyd, was that these excitons, see the photons, when they fall on these are these antenna of the chromophore sites, they are captured here, and they travel very fast to the reaction center where the energy is processed and stored. So Seth Lloyd's group was the first to show that this interference between these multiple pathways, so this is like a small quantum network, and the interference between these 2-3 different pathways may lead to reinforcement of this signal. And of course, this is all happening in presence of the environment. So the environment, of course, is playing a role. In presence of this environment and quantum interference, somehow is helping the photon to exhibit quantum features, and also that the pathway to the reaction center is so efficient. Okay. And within few femtoseconds, it reaches the reaction center. Later on, this Whaley's group used a master equation approach, but they said that there is no speed up in the process, that quantum effects do not lead to the photon necessarily speeding up from the antenna to the reaction center. What could be happening is the efficiency could be, they all reach the reaction center, it's 100% efficient, but it's not that they reach faster. So any quantum effects people were speculating within this femtosecond range will help make the photons reach the reaction center faster. They said that that's not possible. So our motivation when we started this work was to test the prognosis that do quantum effects lead to any speed up of exciton transport from the chromophore sites to, yeah, is there a question?
No, but I think we are very close to the time, maybe 5-10 minutes. Yeah.
Oh, okay. Sure. This is my last work only. I will be finishing in 5 minutes.
Sure.
So our motivation in this work was to test the prognosis that quantum effects do not lead to any speed up of the exciton transport, and we wanted to test whether it's true or not. Now, any quantum speed up is measured by what is called the localization time. And the localization time is defined as the time of the onset of subdiffusive transport occurs in exciton transport. So there is some kind of ballistic or superdiffusive transport, and subdiffusive transport is usually slower, much slower than ballistic or superdiffusive transport. So greater is the localization time, the more is the duration for superdiffusive or ballistic transport. So if quantum features are helping the exciton speed up from initial being captured at some antenna or chromophore site to the reaction center, then for that the localization time has to be large. And the main take-home message of our work is that we see at life-sustaining temperatures, we use what is called a quantum stochastic walk model with pure dephasing, and that we see leads to a quantum speed up in exciton transport. So it depends whether we have quantum speed up or not, very much depends on the theoretical model one uses. That's the main conclusion of our work. So modeling FMO transport. So we give example because we compare our work to this work. This was done by Hoare et al. In this paper in New Journal of Physics. So as I said, that in photosynthetic process, the energy gathered from light by antenna molecules is transmitted across this network of chlorophyll molecules to reaction center, and this process is almost 100% efficient. as almost all the red photons, which are the highly energetic photons, are captured and stored as energy. This is the picture of a photosynthetic complex. These 1, 7, 3, these are the chromophore sites. Generally, the light is captured either at the chromophore site 6 or chromophore site 1, and it is transported to 3, which is where your reaction center is. Okay. This is the position of the site energy at each of these chromophore sites. And we compare first our work to this, the first model which came up to explain this, albeit it was, the first one was by Seth Lloyd. And then this was a master equation approach where they include some lossy terms along with some dephasing, this Lindblad kind of master equation. And they first checked whether they see any coherence. So they checked for total site coherence at both 77 Kelvin and at room temperature, and they see there is some kind of oscillations in coherence if for 77 K, but that eventually completely disappears at 300 Kelvin. Okay, and then they also calculated what is called the mean square displacement, and the mean square displacement is how far or how fast the exciton spreads over the network. That's a measure of that. And there is another measure which is called the power law B. If the mean square displacement, average mean square displacement, can be expressed as in time as a power law, then we can take the log plot of the mean square displacement, and from the slope of that plot, we can estimate what is this power B factor. And this B factor, if it is greater than 1, we call that transport to be ballistic or superdiffusive. And if B is less than 1, then it's called a subdiffusive transport. So basically, the mean square displacement plot depicts how fast an exciton moves away from the initial site. So if you can see in 77 K, the slope of this mean square displacement versus time is much larger than 300 Kelvin. But then at around this 100 femtosecond range, there is a significant dip in the slope. It almost slows down and again it rises. But at 300 K, there is nothing like that. It consistently, the slope maintains its slope. Okay. So when you plot power law B in this Hoare model, you see that the subdiffusive to superdiffusive transition occurs at almost the same time. There's no distinction between them. And that led them to conclude that quantum effects, even if they exist, they don't help in any speed up of photosynthetic transport. So this is the Hamiltonian one uses for this FMO complex. There are 7 sites, and each site has these site energies, and these site to edges. This can be calculated using some spectroscopic analysis, which I will not go into. And from this, using this Hamiltonian, you can plug them into your master equation and calculate the site coherence, mean square displacement, all the things. Okay. So as I said, the localization time is defined as the time at which the transition of power law B occurs from ballistic or superdiffusive to subdiffusive region. And the main conclusion of this Hoare et al. Work was that the superdiffusive transport only lasts for around 70 femtoseconds, which indicates a localization of 70 femtoseconds at both very low, ultra low temperatures of 77 Kelvin, as well as at room temperature of 300 Kelvin. And therefore, they concluded that quantum effects do not lead to any quantum speed up, that excitons don't necessarily move faster because they are enabled by quantum coherence. Okay. So we wanted to analyze the same setup, the same FMO complex, but with quantum stochastic walks. Now, quantum stochastic walks are a amalgamation of classical random walk and the continuous time quantum walk through this parameter which is called omega. So if omega is 0, you get a complete continuous time quantum walk. So I showed you a continuous time quantum walk using with ket psi. So the outer product of psi with itself will give you the density matrix, and the way the density matrix evolves is given by the first term with at omega equals to 0 in time. So if you have just omega equals to 0, you have a continuous time quantum walk. But at omega equals to 1, you have a continuous time random walk, classical continuous time random walk. So with omega, you interpolate between classical as well as quantum. So in the same quantum walk picture, you look at arbitrary omega and then find out what happens when you increase omega. So omega is a measure of classicality in your quantum system. So we find out using the analogy with this Farr et al. Work, what are the omegas? Because here there is no temperature dependence. So omega basically introduces classicality in the system. And there we measure omega, particular omega, which gives the total site coherence as at 77K or at 300K, and then find out at these omegas what happens. Now there are three ways to model these Lindblad operators. One is what is called the quantum stochastic walk with pure dephasing, where you just look at the normalized Hamiltonian with the site energies. You neglect all the off-diagonal elements of your Hamiltonian when you construct these Lindblad operators. In the quantum stochastic walk with both dephasing and incoherence, you look at the whole Hamiltonian regardless of diagonal or off-diagonal entries. And then quantum stochastic walk with only incoherence, you look at only the off-diagonal entries of your Hamiltonian. Okay. So there are three kinds of quantum stochastic walks you can describe: with pure dephasing, with both dephasing and incoherence, and finally with only incoherence. Okay, so I started around say 11:15. So I don't know what's the time now.
12:20.
Okay, so I'm finishing in just 2-3 minutes.
Sure.
Yeah. So omega is a parameter which interpolates between classical time random walk and the continuous time quantum walk. And you have this K, which is a sum over all the vertex sites of your FMO complex. So for the pure dephasing case, you have n vertices because it's only talking about the diagonal entries. For both dephasing and incoherence, you have n square because there are n diagonal and n square. So when you add all the off-diagonal and diagonal entries, we get n square. And for only incoherence, you have only the off-diagonal entries, so it's only n to n minus 1. Okay. Now, for in the omega equals to 0 limit, all three models of quantum stochastic walk reduce to a continuous time quantum walk. While for the omega equals to 1 limit, the only dephasing with incoherence and the only incoherence models reduce to a continuous time random walk. In omega equals to 1 limit, the pure dephasing walk, the quantum stochastic walk with pure dephasing, needs to complete localization. It's not a continuous time random walk, but a completely localized where the you will see d rho I by dt is 0 for I equals to z. That means these probabilities don't change with time, they're just constant. So a pure dephasing model of quantum does not provide a mapping to an exact classical random walk. So this is a weakness of this pure dephasing model. Okay, so when we model FMO using quantum stochastic walk, we plot for each of the three cases. So A is for the pure dephasing, B is for only incoherence, and C is for both dephasing and incoherence. And for omega 0.19, it's roughly equal to the 77 Kelvin, and omega 0.45 is roughly equal to 300 Kelvin. And at both cases, you see very similar picture in both in only incoherence and pure dephasing. While for dephasing and incoherence scattering, you see all the quantum effects have disappeared. Only in the only incoherence, you have quantum effects persisting around 1000 femtoseconds. You can see oscillations in total site coherence. Here also you see oscillations in total site coherence beyond 100 femtoseconds. We again calculate the mean square displacement, and we see that the log-log plot of the mean square displacement from which the slope of which gives us the power law B. Here you can see the localization time. As I explained to you, the localization time for Farr et al. Doesn't change with temperature. Both at 77 Kelvin and 300 Kelvin, they get roughly the same localization time. But in our case, we do get a localization time which is significantly larger at 300 Kelvin than at 77 Kelvin. So this is around 85 femtosecond. This is a 145 femtosecond. That means that quantum effects last longer in pure dephasing picture, and that means transport aided by quantum coherence, you see a quantum speed up. You see, because the localization time is large, that the particles have a ballistic transport or super diffusive transport for a longer time. So quantum effects do come into picture that lead to speed up, but if you have to look at the proper model. So quantum stochastic work with pure dephasing, if this is really happening, can explain that picture. But with other two models, QSW with only incoherence or QSW with dephasing, we in fact get a slowdown. At 300 Kelvin, the localization time is less. Okay. So to understand more, you can go through our paper here. Okay. And I would like to conclude. So quantum stochastic model with pure dephasing is best able to explain not only the robust transport of an exciton, but also the quantum advantage which delivers the necessary speed up to exciton transport. In an FMO complex, of course, there's some weakness with the pure dephasing model. It doesn't revert back to the classical continuous time random walk model, as it ignores exciton relaxation and spatial correlations in the environment. But the quantum stochastic model, regardless of these deficiencies, gives the speed up at 300 Kelvin as compared to 77 Kelvin, while both quantum stochastic work with only incoherence and that with both dephasing and coherence gives slowdowns. Okay, so that ends my talk, and I would like to thank all my students and collaborators. Many of their papers I explained. Of course, Dinesh is a PhD student. Nani, Pravi, Abhishek, Pratyushan, Varun, and Jishnu are all master students or were master students working with in our group. Okay, so thank you very much.
Yeah, thank you, Professor Colin. So now the floor is open for questions. Since we are constrained of the time, maybe we will take only one or two questions. Yeah. Okay, if there are any questions from the audience, you can unmute the mic or raise the hand. Okay, okay, there are no questions. Maybe I will ask one quick question. So in the FMO complex, the dimension of the complex and the coherence of the light play any role, or they are not?
Yeah, see, FMO complex generally are with 7 vertices. And there are different kinds of FMO complexes. So this is what is called the C. tapidium bacteria. FMO in a C. tapidium bacterial complex, this one. There is a P. asturi also. That's also a bacterial complex. So these are small bacterial complexes which can be easily dealt with. And there are huge number of chlorophyll molecules in other more complicated algae and fungi. And of course, plant and animals that goes beyond. But we look at small types of such systems to understand them better. So if you look at both P. asturi and C. tapidium, in fact, we are working on that. There is hardly any difference as far as exciton transport is concerned. There may be some marginal differences, but there is hardly any difference regarding localization time or the mean square displacement or of those things. So this was one question. What was your other question?
No, does the spatial coherence of the light and the dimension plays any role?
No. Here we are taking photons. They just come, strike the chromophore, and generate excitons. So regardless of what will play a role is where they strike. For example, you take the initial site as 6, then the dynamics are slightly different if you take the initial site as 1. And of course, there have been many papers in FMO complex which take superposition between 1 and 6 also. So light simultaneously striking 1 and 6 chromophore sites, generating a superposed exciton state between chromophores 1 and 6, and how they then dynamically evolve, how fast they go to the reaction center. That's, of course, another study. Our main study was to compare our work with some previous works, which predicted there would be no the quantum is not playing any role leading to any speed up. And we saw that they were partially right, because this is completely model dependent. Looking at a theoretical model, you can come to completely opposite conclusions. If we look at quantum stochastic work with say pure dephasing, you come to one conclusion. While we come look at QSW with only incoherence or dephasing, we come to a completely opposite conclusion. So depending upon the theoretical model you use, you come to distinct conclusions. So that's the main purpose of our study.
Yeah, thank you.
Thank you so much.
Yeah, if there are